learning how to balance redox equations, which is a little bit more complicated than normal balancing of equations. We're going to be learning two different methods. One is for balancing redox equations under acidic conditions, and then in a few slides we're going to talk about how to balance them under basic conditions. Now, the problems themselves are going to be saying whether you have to balance them under basic or acidic conditions. So you don't need to know that. That will be told to you. All right, the process that we're going to follow is written here. So the first thing is that we're going to take our redox reaction and we're going to separate it into half reactions, one for the oxidation, one for the reduction. For each of the two reactions, we're then going to do the following steps. The first thing is that we're going to balance the elements that are not hydrogen or oxygen, for example, sodium, potassium, manganese, etc. After that, and we're going to balance that by using coefficients. After that, we're going to balance oxygens by adding water. So in any side where you need oxygens, you're going to be adding water, one water for each oxygen needed. In the next step, we're going to balance hydrogens. So for each hydrogen that you need, you're going to add H pluses. H pluses accounts for the fact that we're balancing under acidic conditions. After that, we're going to look at the charges on each side of the equation, and we're going to balance the charges by adding electrons. Finally, we're going to look at the two half reactions, which have already gone through steps 2 to 5, and we're going to balance the number of electrons between the two half reactions, meaning that we need to have the same number of electrons on either of the two reactions. And we're going to do that by applying a coefficient multiplier. Basically, we need to make sure that we have the same number of electrons, so we're going to find what's the lowest common multiple of electrons, and we're going to multiply one or both equations by a number to make it be the same number of electrons. Step number 7 is that we're going to add the two half reactions, and then at the end we're going to check to make sure that we have the same number of atoms for each element and the same charges on the left and on the right of the equation. Now, notice that there's an alternate method that is introduced in the book in table 19.1. I'm not going to go over that method, but that method would lead you to the same result. It is just slightly different, and you might find it more difficult or easier. I'm not sure. So just wanted to let you know that there's another method. Don't get confused. Again, both methods are different, but they both will give you the same result. All right, let's go ahead and try this out. So have this next to you so that you can actually follow as you go. I forgot to mention, so I have the same steps here, but written with a little bit more words in case that it helps you. But I don't usually go over these in lecture, so I'll just have those there for you in case that it helps. So let's go ahead and do the example. Balance the following oxidation-reduction reaction that occurs under acidic conditions or acidic solution. So what we're given is the full redox equation, but it's not balanced, and we are told that it is in acidic solution. Remember that the first step was to separate it into the two half reactions, one for the oxidation, one for the reduction, and we don't need to know right now which one is the oxidation and which one is the reduction. The easiest way to do this is to look at what compounds or ions have the elements that are not oxygen or hydrogen. So for example, I'm going to be looking at my arsenic here and arsenic here. That means that this goes with this. And then the other one is nitrogen. I have nitrogen here and nitrogen goes with this one. So those are going to be my two half reactions. So we begin by putting As2O3. And that one is going to go into H3AsO4. All right, the other half reaction is taking that nitrate and O3 minus, and that one is going to go to NO. All right. Right, so that was the first step. The second step is that we're going to be balancing the atoms that are not oxygen or hydrogen. So that means that in this case, we're going to be balancing the arsenics. I have two arsenics here. I have only one here. Therefore, I'm going to add a coefficient of 2 to make them the same number of arsenics. On the bottom, I have nitrogen. One nitrogen here, so those are done. The next step is to balance the oxygens by adding water. So I'm going to count the number of oxygens right here, and let me go ahead and change color, sorry. On the left-hand side, I have a total of 3 oxygens. On the right-hand side, I have a total of 4 times 2, which is 8. So 8 oxygens here. Here we said that we had 3. What am I missing? What am I missing? That's it. So I need to make them the same. How do I do it? I'm going to add as many waters as I need oxygens. I need 5 oxygens on the left-hand side, so I'm going to go ahead and add 5 waters. All right, and if you don't mind, I'm going to go ahead and delete this number and this number just to not confuse myself. All right, on the bottom, we're going to do the same thing. We're going to be looking at the number of oxygens. I have 3 on this side. I have only 1 on this side, which means that I need 2 more on the right-hand side, and that's going to be by adding 2 waters. Again, each of the waters comes with 1 oxygen, so we add 1 water for every oxygen that we need. The next step is to balance the, the hydrogens by adding H pluses. So I'm going to look at how many hydrogens I have here. In this case, 5 times 2 is equal to 10 hydrogens. On the right-hand side, 2 times 3 is equal to 6 hydrogens. To make them the same, I need to add 4 hydrogens on the right-hand side, and they are added as 4 H pluses. H pluses indicating that we're balancing under acidic conditions. And again, if you don't mind, I'll go ahead and delete this number and this number so as to not confuse myself. On the bottom one, I have no hydrogens on the left, but I do have a total of 2 times 2, which is 4 hydrogens on the right. That means that I need a total of 4 H pluses here. All right, the next step is to balance the charges by adding electrons. What that means is that we're going to be adding electrons to the side that is more positive to bring it down to be the same number as the charge of the other side. For example, here, my charge on the left-hand side is equal to 0 because there are no positives or negatives. But on the right-hand side, I do have charges. I have a total of 4 positives. 4 times positive, that's 4 positives. And this is my more positive side. So I'm going to be adding electrons to that side to bring it down to 0, in this case to 0 because the left is 0. That means that I need to add a total of 4 electrons right here. Again, the way that I do it is that I count the charges on both sides. Whichever side has the most positive charge, that side is going to get electrons and is going to get as many electrons as is needed in order to bring the charge down to be equal to the left-hand side. In this particular case, that was a 0, but it doesn't have to be 0. They just need to have the same charge. So now in this particular case, both sides have 0 charge. On the bottom, my left-hand side has a -1 charge, and here we have 4 pluses. So 1 negative minus 1 plus 4, that's equal to a total of 3, charge of 3. And on the right-hand side, I have 0 charges. That means that this side is more positive. That means that I'm going to add electrons here. And the number of electrons is going to be 3 to bring it down to be equal to the right-hand side. So 3 electrons here. And again, I'm going to go ahead and erase this to not confuse myself. The next step, remember, is to go ahead and balance the charges between the 2 half equations. So in this particular case, I have 4 electrons here and I have 3 electrons here. To make them be the same number of electrons, I need to find the smallest common multiple between the two. And in this case, that's going to be 12, right? That's the smallest number that both of these can divide. So 12. And to do that, I'm going to be multiplying this whole equation times 3. And I'm going to be multiplying this whole equation times 4, such that I get to 12 electrons. And so now I'm just going to come and rewrite my whole equation here on the bottom, each of the equations. And I'm going to begin with the arsenic. So 3As2O3 plus 5 times 3 is 15 waters. And then arrow, 2 times 3, that's 6H3ASO4. 4 times 3, that's 12 H pluses. 4 times 3, that's 12 electrons. Then on the bottom, 4 times 1, that's 4 NO3 minuses, plus 4 times 4, that's 16 H pluses. 3 times 4, that's 12 electrons. Then I have my arrow. Oops, that is not an arrow. Ugh. Okay. Then I have 4 nitrogen monoxides. And then 2 times 4 is going to be equal to 8 waters. I cannot do 8s on this thing for the life of me. All right. The last step is to add these two equations. And to do that, what we're going to be doing is that any things that are on opposite sides are going to subtract one another, while things that are on the same side are going to add up with one another. And the first thing that I usually begin with is by looking at my electrons, because I know that I forced them to be the same number of electrons. Otherwise, otherwise I did something wrong. So I have 12 electrons here and 12 electrons here. They're on opposite sides, so they subtract one another, and that means that they cancel away. From there, I'm going to start looking at my first thing here. Do I have that anywhere else? AS2O3? I do not, so I cannot cancel it with anything, so it comes down. 3 AS2O3. And if you don't mind, I usually like to highlight the things that I have already taken care of so that I don't redo it. The next thing is my waters. I have 15 waters here, and I also have water on the other side, 8. Since they are on opposite sides, they subtract one another, so 15 minus 8 is equal to a total of 7 waters. Right? And I have taken care of my waters. So I'm going to go ahead and highlight and highlight. All right, the next thing is on the left-hand side, I have these nitrates, and those nitrates are nowhere else, so they're going to come down as they are for NO3 minuses. And I can go ahead and highlight my nitrates. Then I look at my H pluses. I have 16 here and I have 12 here. So 16 minus 12 is equal to 4. And that means that I'm going to have 4 H pluses here. Then I have my arrow, and I'm going to highlight my hydrogen ions before I forget. And then on the right hand side, I have 2 things that are left that I cannot cancel with anything else, so I can just come and bring them down. 6H3ASO4 and 4NO. The last step is to kind of double check, make sure that you have the same number of atoms and the same charges on both sides. For example, for my arsenic, I have 3 times 2, which is equal to 6, and on the right I have a total of 6. Let's say my hydrogens. Here I have 7 times 2, that's 14, plus 4, that's a total of 18. And on the right hand side I have 6 times 3, which is 18, and so on and so forth. Looking at the charges at the same time, I have 4 negatives and 4 positives. That means that is 0 on the left hand side, and on the right hand side I have 0. So all of your atoms and all of your charges need to balance on the left and on the right. That's it. We are done balancing the equation. The last thing that I wanted to come and let you know is that on our first 2 equations, we are now able to figure out which one was the oxidation and which one is the reduction, in that one of them has the electrons on the product side. That means that we are losing electrons. That means that this right here was our oxidation, because we lost electrons. On this side, on the other hand, the electrons are on the left-hand side and the reactant side. We are adding electrons. We are gaining electrons as we go to the right. That means that this is our reduction. So that's one way of figuring out the oxidation and reduction. We could have also figured it out by looking at what happens to the atoms. In this case, like the arsenic here is going to be changing oxidation number. And on the bottom, the nitrogen is going to be changing oxidation number as well. The last thing that I want to mention is that in every single case, your electrons need to be on opposite sides. If for some reason you end up having the electrons on the same side, that means that you have done something wrong. That means that you need to start all over again, or check what you have done. Electrons in one equation are going to be on the right side of the arrow, and on the other equation they need to be on the left side of the arrow. If you have them on both sides, that means that something is wrong. All right. For the next example, I'm actually not going to do it. I'm going to have you guys do it yourselves at home. I give you the answer, which is here at the bottom. So please do it. Please check yourself. Make sure that you're following the steps. If you run into any problems, please feel free to email me and I'll set up a Zoom meeting and we can work through it together. Also recommend that you look at examples, that you actually try the problems on example 19.3 and problem 19.3, but don't necessarily look at how they did it because again, remember that they're using a different method and that might confuse you. So just try to apply the method that I taught you here using those problems and make sure that you get the same answer. All right, so question for you guys. For the following partially balanced half reaction, how many water molecules must be added in order and to which side of the reaction in order to balance? So how many water molecules and to which side, left or right hand side, reactants or product side, in order to balance the equation? Give it a try. All right, so how do we do this? Basically, what we have to do is that remember that as you're balancing these equations, we first balance the atoms that are not hydrogen or oxygen, right? So the carbons, and that's already been done. We have 2 and 2. The next step is to balance the oxygens by adding water. And so we have to count how many oxygens we have on the left, how many oxygens we have on the right, and make sure that they're the same. Wherever we need oxygens, we're going to add waters. So on the left-hand side, I have a total of 4 oxygens. This 2 minus is the charge. It has nothing to do with the number of oxygens. So I just have 4 right here. On the right-hand side, I have 3 times 2. So I have a total of 6 oxygens. That means that I need to add 2 oxygens to the left, which means that I have to add 2 waters to my reactant side. And so the answer was C. I hope you guys got it. Now, I usually tell my students to go ahead and finish balancing this half reaction. After the oxygens are balanced, the next step is to balance the hydrogens. So on the left-hand side, I have 4 hydrogens. On the right-hand side, I have 0 hydrogens. That means that I need to go and add 4 H pluses on my right-hand side. From there, the next step is to look at the charges, right? And to the charges, we are going to start by counting the charges on the left-hand side. This doesn't have charge, but this right here does, right? I have 2 negative charges with a coefficient of 1, so that's a total of 2 negative. And if you don't mind, I'm going to delete these numbers because that's just confusing me. All right, so again, on the left-hand side, I have negative 2. On the right-hand side, I have negative 2 for each of these, but I have 2. That means negative 4 here, and here we have positive 4. That means that on the right-hand side, I have a total of a charge of 0, but on the left, I still have a negative 2. So to balance it, I need to add electrons to the more positive side between negative 2 and 0. Which one is more positive? The 0 is more positive. So I add electrons here. How many electrons? That would have to be a total of 2 electrons to bring it from a charge of 0 to a charge of negative 2. Again, what we're trying to do is make the left and the right be equal, not necessarily be negative or be 0. They both just need to be equal. In this particular case, by adding these 2 electrons, that makes the right-hand side be equal to negative 2, and the left is negative 2 as well. All right, so now, this is how we balance equations under basic conditions. You'll see that the process is almost the same, except for step number 5 and 6, which are highlighted in red. So first step, we're going to write our half reactions, one for oxidation, one for reduction. We're then going to balance elements other than hydrogen or oxygen. We're then going to balance our oxygens by adding waters. We then will balance the hydrogens by adding H+. Then we need to neutralize all of the H pluses by adding the same number of hydroxide ions to both sides of the equation. Notice this thing about both sides of the equations. That means that, for example, if I had 4 H pluses on one side, I will be adding 4 hydroxide ions to the left and 4 hydroxide ions to the right. That means I have the same number of hydroxides as I had H pluses, but I add them to both sides of the equation. We will then combine any H pluses and OH minus that are on the same side, and they're going to come together to form waters. So basically what we're doing is that we're neutralizing any acid to make it into water, and instead we're going to have leftover hydroxides on the opposite side. Those hydroxides indicate that we are balancing the reaction under basic conditions. After that, we go back to the normal steps or balancing the charges with electrons, and finally multiplying the half reactions with a coefficient as needed to have the same number of electrons on both, and finally adding those two half reactions and checking. All right, let's go ahead and give it a try. Again, I leave you here more details in case that it helps, but we'll go ahead and get started on a problem. So balance the following oxidation reduction reaction that occurs under basic conditions. All right, so step number 1 is that we are going to separate this into two half reactions. And again, you can just kind of look at the elements. We have C and N, carbon and nitrogen, that's one equation. The other equation has the manganese and manganese. So I'm going to take my Cn minus and is going to go to the right hand side as CnO minus. The other one is going to be my permanganate ion, MnO4 minus, and that's going to go to form, whoops, that arrow is a little funky. It's going to go and form, okay, it just does not want to do arrows right now, MnO2. All right. So remember that the first thing that we want to do is to balance the elements. So carbon and nitrogen, there's one of each of them, they are good. On the bottom, my manganese and my manganese is 1 and 1, they are good. The next step is to balance the oxygens by adding water. So basically on here I have 0, but here I have 1 oxygen. That means that I need 1 water here. Just one of them because each water brings 1 oxygen. Oxygens are good. On the bottom one, I have 4 oxygens here, and I have a total of 2 here. That means that I need to add 2 more on the right-hand side to make it equal. So 2 waters to go ahead and get the oxygens set up. And again, if you don't mind, I'm going to delete my accounting here to not confuse myself. The next thing is that we're going to be balancing the hydrogens by adding H pluses. So on the top, I have 2 H pluses and I have 0 here. That means that I need to go ahead and add 2 H pluses right here. On the bottom, I have 0 hydrogens here, but I have a total of 2 times 2, which is 4 hydrogens on the right-hand side. To make them the same, I need to add 4 H pluses here. All right, cool. So this is where things change a little bit, right? What we're going to do is that wherever we have H pluses, we're going to go and add the same number of OH minuses, but we're not going to add the OH minuses only to that side. We're going to add the same number to the other side. So for example, here, I have 2 H pluses here. That means that I'm going to go and add 2 hydroxides here, and I'm going to add the same number of hydroxides here. If we don't add them to both sides, we would be basically messing with the number of oxygens and hydrogens again, and everything would be unbalanced. So we have to make sure to add them to both sides. We do the same thing on the bottom. I have 4 H pluses. That means that I need 4 OH minuses here and 4 OH minuses on the, undo, 4, please write, come on, H minuses on the right hand side to make them the same. The next step said that we were going to combine all of the H pluses and OH minuses that are on the same side and turn them into water. And I can do that kind of easily here because I can delete. So basically these two right here combine to form 2 waters. And if you don't mind, I'm just going to go and delete them and combine them into a total of 2 waters. Okay. From there, we're going to do the same thing on the bottom. On the bottom, I have my H plus NOH on the left-hand side. So I'm going to go and delete those two. They are the same number because we made them the same number. And those are going to come together and form 4 waters because I have 4 H's and 4 OH's. They become 4 waters. All right. We're back in business. Now we go back to the normal steps, which is the next thing is to balance the electrons by adding, balance the charges by adding electrons. So we're going to count our charges. On the left, I have 1 negative and 2 more negatives. That means that I have a total of -3. On the right-hand side, I have a total of -1. There's no other charges. How do I make them equal? I add electrons to the more positive side. Which side is more positive? The right-hand side. How many electrons do I need to make it the same as the left? I would need 2 electrons because -1 and 2 more negative charges gives me the -3 that I need. And I can go ahead and delete those numbers now. Oops, that is not delete. Here we go, delete and delete. Okay, on the bottom we do the same thing. We count our charges. I have here a -1 charge. And on the right-hand side, I have a total of 4 negative charges. So I'm going to add electrons to the more negative side, the more positive side, which is this guy. And how many electrons do I add? I add 3 electrons to make it be the same as that on the right-hand side. I have a total of -4 charges now and -4 charges, and I am good. I can delete my accounting. Oh, for God's sake. All right, what is the next step? The next step is to get the same number of electrons on both of the equations, right? And to do that, we're going to find the smallest common multiple of those two. I have 3 and 2. The smallest common multiple is going to be 6, which means that I need to multiply the top equation by a total of 3. To make it 6 electrons, and the bottom one would have to be multiplied by 2 to make it 6 electrons. And I'm now going to go and rewrite those equations on the bottom. Let me move a little bit lower here. All right, so I'm going to rewrite this. The first one becomes 3 Cn minuses plus 3 waters plus 6 hydroxides. Great, it's not letting me write again. 6 hydroxide ions goes to 3 CNOs minuses plus 6 waters plus 6 electrons. Awesome. Now we do the same thing to the bottom equation. So the bottom equation, we have 6 electrons now plus 2 MnO4 minuses plus 4 times 2 is 8 waters. And then we have our arrow, and then we have 2 MnO2s. Nope, that's not what I want. 2. Ay, Dios mío. Plus 2 times 2, that's 4 waters. And 2 times 4 is 8 hydroxides. All right, now we have to start canceling things out to be able to add our equations. And remember that the first thing that we cancel away is the electrons because we know that we already set them to be the same number so that they cancel away. 6 electrons are being lost, 6 electrons are being gained, right? So they go away. We then begin with our Cn minus. That one doesn't seem to be anywhere else, so I'm just going to go ahead and take it down here, 3 Cn minus, and I highlight to ensure that I show that I've already taken care of it. The next thing is my water. I have 3 waters here, and I have 6 water here, and 8 here, and 4 here, so I have a ton of water, right? So 3 plus 8 is equal to 11. And on the right-hand side, I have 6 plus 4 is equal to 10. That means that I'm going to be left with a total of 1 on the left-hand side. So I'm just going to come and say plus water here. And all of the waters are taken care of. And I can go ahead and highlight the 3 waters, the 6 waters, the 4 waters, and the 8 waters. They are all taken care of. From there, the next thing is my hydroxides, I guess. And I have a total of, let me delete this. I have a total of 6 hydroxides on the left and 8 hydroxides on the right-hand side. That means that I'm going to have 2 left on the right-hand side. So I'm going to go ahead and put 2 hydroxides and done with the hydroxides. 2 and 2. The next thing that I have on the left-hand side is my permanganate ion, and there's nothing like that anywhere else, so I'm going to go ahead and just bring it down. 2 MnO4 minuses. We are done with the left-hand side. Now on the right-hand side, I have just 2 leftover things that cannot be canceled with anything, so I'm just going to bring them down. I have 3 CnO minus plus 2 MnO2. And we are done. The last thing, really, you just need to check to make sure that everything balances away. So for example, my carbons, I have 2 carbons on both sides. My nitrogens, I have 3, I have 3 carbons. I also have 3 nitrogens. I have 2 manganeses, 2 manganeses. My oxygens, I have 1, and here there's 8, so 9 on the left. And on the right-hand side, I have 2 plus 3, that's 5, plus 4, that's 9 as well. And then the charges. On the left-hand side, I have 3 negative and 2 negative. That's a total of 5 negative on the left-hand side. On the right, I have 2 negative and 3 negative. That's also negative 5. So we are good. That is your balanced equation under basic conditions. Just to remind you what we did different, basically whenever we were left with H pluses, we added that many number of hydroxides, but we added them on both sides. Like here we had 2 H pluses, so we ended up adding 2 hydroxides here and 2 hydroxides on the left. We then combined the hydroxides and the H pluses to form water. That's the only thing that we did differently. The other thing that I want to mention again, we need to have the electrons on opposite sides. And by looking at the position of those electrons, we can figure out which reaction is the oxidation, where we are losing electrons, which is this case, and which equation is our reduction, where we are gaining electrons, because the electrons are on the reactant side. So this is my reduction. All right. There's another example that I'm not going to do in the lecture. I recommend that you guys try it yourself. This is the answer. There's also additional examples and practice problems in the book that I recommend that you try. Remember that they are using a different method, so just try it with the method that you have learned and see if you get the same answer. All right, we're going to go over a couple of concepts to get us ready for the next section. So electricity. For electricity, there's 2 concepts. One of them is electrical current. Current is usually written as the letter I. Actually, you will see it in an equation later on as capital I, if I remember correctly. Electrical current is basically the flow of moving charges. One example of current is going to be electrons moving through a wire, or another example is ions that move through a solution. Both of those are examples of electrical current. Current is measured in amperes, which are symbolized with the capital letter A. Now, the other concept is potential, and in this class, you're going to be seeing potential as a squiggly E, if you would, or an epsilon. The potential is the force that pushes charges to actually flow. So it's basically the driving force for electrical current to occur. We also call it the electromotive force, or basically the driving force to enable a current to take place. It is also called voltage, and because of that, we're going to be measuring it in volts, or capital V. Now we're going to be talking about 2 different types of electrochemical cells. One of them is called a voltaic cell or galvanic cell, and then a different one is called an electrolytic cell. So be careful with the name. Electrolytic doesn't mean, is not the same thing as electrochemical. Electrolytic is a type of electrochemical cell, okay? The electrochemical cells have two different types at least. All right, so voltaic cells or galvanic cells, they're going to be using a spontaneous chemical reaction to generate electricity for us. On the other hand, the electrolytic cells are going to be utilizing electricity in order to drive a non-spontaneous reaction to occur. So the left one gives us electricity. We're using a spontaneous reaction to give us electricity. The electrolytic cell, on the other hand, we are forcing a reaction to take place by driving it through application of an electrical voltage. All right.